So I will be presenting you the next this talk on the ranking and selection of geological stores. I will introduce you the place of this work within the Hystories project, explain why do we need to rank and to select underground storage sites, and also then why do we also need to define cases for underground storage cycles, and then go through the results we got on cost and on also a suitability mark we developed, and conclude. So the place of this presentation in the project, it's kind of at the center of it, and the project was even a little built for that, because it's reusing a lot of very good pieces of work that have been done by others in the project. And so it was quite pleasant to, this work is kind of assembling a puzzle, and it was quite pleasant for Jan and myself to kind of assemble these great pieces of work. So we deserve really the credit for the assembly, and yeah. So we are reusing the extensive trap database and data collection from Work Package 1, Kerry exposed. We're reusing the fact that normal carbon steel looks acceptable for building underground and surface facilities for underground hydrogen storage sites, new ones. So we don't consider a cost of stainless steel. We're reusing also quite a lot results from and the ranking scheme Martin presented yesterday from the microbiological work. We're using also extensively the capacity estimation Jan exposed yesterday. We're reusing also a lot LBST's results on energy modeling on the energy modeling work of Hystories to define the cycles we will use. And last, it's really interrelated with the cost model we just presented. It's an application of it. So why do we need to rank and select these sites? So Jan presented a very close image yesterday. So it shows here the bars are depending on the scenario. That's why it's a bar. Depending on the scenario by LBST, it is the underground storage demand in terms of capacity, and the green dot is the exact same value as Jan presented yesterday. So it is the technical capacity or storage resource, as Jan named it, found by Hystories. And it's a new result. It's based on the WP1 data collection. I think it's really new at the European scale. It wasn't there before Hystories. And for salt caverns, which was not, as said in the introduction, a topic of technology development for Hystories, we have been reusing published data essentially, with a few modifications by Geostock. And what we see are the dots. If you look at EU27 plus UK, the capacity in identify in salt and in porous media is orders of magnitude higher than any of the scenario found by LBST in 2050. It's actually 40 times higher in salt and 12 times higher in porous media. Only looking at offshore. We didn't even took the offshore numbers because it was already good enough. So because we've got this technical capacity that is much higher than what demand can be, we focused on onshore, and we also have a need to select the best site. And so we are proposing a way to rank and select underground storage sites. For that, we developed two indicators. One that is the levelized cost of storage. It is a break-even selling price of the storage service. So it considers over the life cycle of the facility the capex discounted and also the discounted of the storage use in the denominator here. And the other indicator we built is a suitability mark. It reflects the technical readiness of this underground storage technology given the knowledge we have. So if it's low, it's not necessarily that it is not suitable. It is with the knowledge we have, it's not that suitable. And also it is built to be complementary with the cost indicator. So, for instance, if a trap is 5,000 meters deep, it's actually not very suitable. It's too deep, but this is reflected in the cost. If it's a very poor permeability, this is also reflected in the cost through the number of wells we estimated. So it is an indicator that is built to be complementary. So it is an approach that has its limits. First, we decided to limit that to onshore storage. We also had some limitations that were in the cost model that was presented right before. For instance, it stops at only 3 compression stages. So if you're deeper than let's say 3,500 meters about, it's not the model is parametric, but not to this point. Also, the cost model we presented is parametric, so it's adaptable to a large number of conditions, but it was based on a conceptual design main case, typical case, and if you're going really orders of magnitudes higher or below this, it starts not being that good. You would have to consider a different number of rigs you deploy in parallel. You have to rethink your project, and it's a kind of new feasibility of the project, and we cannot be that generic. So we had to introduce some limitations to the application, capping the maximum capacity to the conceptual design we defined, which is already a quite large underground storage site, and also a maximum kind of reasonable compression flow rate for a site. If it's bigger than that, we consider it's like developing 2 sites. So keep in mind that if it's much higher or smaller than the conceptual designs we define in deliverable 7.1 you can find on our website, then maybe there are optimizations or cost increase to consider. And also we had to tackle the cost of the question of cost estimate of converting existing sites, which is even more site specific. So for that, we consider that this existing site, typically underground natural gas storage, but also it could be an existing brine cavern, an existing depleted field that also already have some wells drilled. So in this case, we consider that we re-drill the wells, we re-leach the caverns, etc. Because this asset, existing one, is also worth something. So you cannot ignore that and just account for the conversion costs. And also it was easier to apply our model. So now I will go through why do we need to define cycles. So these are 2 sites I had a chance to visit or work on. And it's kind of funny because from the underground point of view, it's almost similar. There are 6 caverns 6 caverns in the first one, 7 in the second one. So caverns in both cases, 1,000 meters deep in both cases, almost exactly the same capacity. So from a capacity point of view, it's really similar. From a pressure point of view, it's the same. But here you see there are 6 compression buildings. There are 6 compressors. There are 12 megawatts, I think, of compression power. It's considered as a fast cycle storage site. And this one, before extension projects, there is only 1 compression building. I think it's 0.5 megawatts power. And it's totally different from a surface point of view. And it is what we said. If you only look at the capacity, sites are really so similar. But if you look at what it looks like from a surface, and surface is a big part of the cost, it is very different sites, not the same scale at all. So that's why if we look at the LCOS, the levelized cost of storage, you have to consider the cycle or for instance, the discharge duration. It's also what other studies did here. The hydrogen report by IEA, for instance. You see the LCOS, levelized cost of storage, is changing a lot depending on what discharge direction, what cycle you choose. And you don't find, depending on cycle, if you discharge in 1 hour or in 1,000 hours, the cheapest technology will not be the same. So we have to look at what cycle should we consider for hydrogen underground storage, which does not exist for green hydrogen today industrially. So if we look at analogs of underground storage, CO2 we want in, we don't want in out, it's different. Oil is stored mostly for geopolitical reasons for many years. Natural gas, it started to be stored for seasonal, to cope for seasonal fluctuation of the demand, and it's still the main driver today. So it's mostly seasonal cycles, even if there are maybe new cycles too. And also some LPG or hydrogen storage as known today. It's a buffer for the industry, so it's also mostly stored for many years. So you've got underground storage cycle here, really seasonal cycles in the geomethane storage sites. And here you've got the air liquid hydrogen storage cavern in the US. You see the cycle, and it's also stored over a few years. And what about green hydrogen? Well, we don't really know the drivers. Mainly, there are actually it's a combination of many. It depends on whether you store for power to mobility, power to industry, etc. So it's not that easy to have an expert opinion. So that's why we rely on modeling and experts from LBST and their modeling work. So I'm replotting the picture for France in 2050 Christopher just presented. So it shows you first a maximum for this country. So here it's a case of France, but the cycle I will develop are given with European average values. So it gives you the storage demand. So that's the numbers that were compiled in the charts that was presented in his conclusions. But we don't use only this information for designing storage sites. We also have to use the equivalent number of cycles per year. So you see here it was said there are a seasonal pattern and also a lot of shorter term cycles. So that's why in short we've got 1.9 full cycle equivalent per year. And here we've got only one cycle, no cusp, very clear. You see here too that we've got a lot of standby time. Here we've got almost none. So that's why you've got different load factors. You see that if you make the ratio of the storage capacity, so this value here, to the slope you have when withdrawing, this slope here, you've got the number of days you need to totally empty an initially full site, and that's a good indicator of the how fast is your cycle. So for here we define this seasonal cycle with a withdrawal capacity of 115 days, and here withdrawal capacity of 18 days only, a fast cycle. And you also have to distinguish. We also introduced a ratio between the withdrawal capacity and the injection capacity, and same we found a ratio of 1 for the seasonal cycle, same slope here and here, and of 2 for fast cycles. So you can withdraw at a flow rate that is twice higher your injection capacity. So we needed all this actually to define our cost estimate. We also chose to focus on only one of the scenarios that were developed in our package 5. We picked scenario D, more coherent with the Repower EU plan, to define this seasonal cycle on the left and fast cycle on the right. So there were results given for a given technology in our package 5. However, in a country, if you've got the two options, where you can choose, it's also site specific, and you're not bound to use one technology or the other, provided that the two are technically feasible. So we've defined these two. Cycles. So these are the results for the first cycle, the seasonal one, and we applied the cost model to all the 900 or 800 traps with their own characteristics like depth, permeability, etc. And we applied the parametric cost model that was presented for this cycle. So it gives us one cost. So this is 1 point you see here. Here you don't see that very well, but there are 800 points. And so each porous trap has a given has one single levelized cost of storage that has been estimated through this parametric cost model applied to the parameters given by the geological data and the capacity estimation data. So this is for porous media. We find that for seasonal storage, you see, and yes, and we also did that for salt caverns. So we, because on the right part of Hystories, if you remember, salt caverns are also included because we cannot draw estimation of our outlooks on the deployment of underground hydrogen storage without considering them. So we also applied the cost model to 19 bedded salt deposits throughout Europe and 2 salt domes in Europe using the SMRI database work. So we find that for these seasonal cycles, in many of the countries, depleted or aquifer porous storage are cheaper than salt caverns. This is the result we got. It's quite coherent with natural gas storage as known today, mostly driven by seasonal cycling and mostly developed in porous media. We also find that we've got a very high range, so it's a logarithmic scale here. We've got a very large range of cost, especially for porous media. It's related to the geological diversity of these 800 traps and parameters we have. It's also related to the fact that we've got a lot of small traps, especially for some countries like Spain, in the database. And underground hydrogen storage, or underground storage in general, actually, is quite upscalable. It's an upscalable technology, but it's not a very downscalable technology. So cost gets higher when you want to make small projects. So that's why we introduced in our results the cost. So same x values as the one that were presented before, but we plotted that against the capacity. And what you see here is our 800 points with for porous storages with their capacity in the x-axis and the levelized cost of storage we found. So this is for seasonal cycle again. The fact when you've got the point here, it is the maximum capacity of the trap as computed, is high-level estimation. You can imagine developing it at a lower level. You don't necessarily have to reach this point. For salt caverns, but we have kind of a maximum value. We have a data for putting that in this x-axis. For salt caverns, salt deposits are so large. In the 19 we considered, you cannot really, and it's really engineered. You will choose and design the number of caverns you want. So we did not have had a clear X value to define. There is no real way you can define that. So that's why for salt, we have chosen to display that with lines, solid lines. But so you find it, and the conceptual model we had are around here for salt and for porous media. It was a 250 million cubic meters for salt and 550 for porous media. So these are the results for cost we got for the seasonal cycle. Now this is the result we got for fast cycles. So same methodology, different cycle, different surface facilities mostly, and also different number of wells for porous media. So you see the change. So this before was still the same result for seasonal cycle, and you see the change in the way the dots are spread and the lines are when you move from seasonal to fast cycles. So what we find is actually the two technologies, due to their cost structure, differ a little bit. We find that it gets a little bit cheaper, the levelized cost of storage for salt, and it gets more expensive for porous storages when we go to fast cycles. So this is due to the fact that we've got an impact on the subsurface cost on porous media when we go to fast cycles, higher number of wells, whether it's unchanged for salt caverns, and also that in general the surface cost increases when we go toward fast cycles, and the share of the surface cost was higher for porous storages than for salt caverns. So then we looked at what would be the cost if developing the cheapest of these points, the cheapest of these sites, either in salt or in porous media, until we reach the maximum capacity or demand found by the energy modeling work in any of the scenarios. So it was 325 terawatt hours. And so if we develop the sites until we reach this capacity, we find these values. So we find that the levelized cost of storage would be 1.1 euro per kilo for seasonal storage in porous media, and and for fast storage it would be 2.6 kilograms. And for salt caverns, 2.3 kilograms here for seasonal storage, 2 euro so 2.3 euro per kilo for seasonal storage, 2 euro per kilo for fast storage. So depending on the cycle, we find back, but it was not meant for that, a result that looks intuitive for people in this industry, but that salt caverns are more expensive for seasonal cycling. But are less expensive, a little less expensive for fast cycling. So now I'm getting to the suitability marks. So as said, it is built to be complementary to the information that is already reflected in the cost. So the information in here is mostly readiness level as identified in WP2. The type of lithology of the seal, whether it's salt, whether it's sandstone, etc. Whether we know that there are faults crossing the reservoir, the number or the presence of abundant wells in this reservoir, and the application of the risk ranking chart of the microbiological one, with the data we had. And also a lot of expert opinion from Jan for all the porous media behind that, because the data was not always complete. So it was done for porous storages, so the 800 points again, and also for salt caverns. So if we want to draw very basic conclusion, we find a higher suitability mark for salt caverns, notably because there is not the microbiological risk at the same level, and because it's also a technology that has more experience for hydrogen storage. And for porous storages, points that are ranked higher are mostly existing underground natural gas storage that have already proven that they can be used for trapping and storing gas underground. So these are our conclusions. So with these high-level estimations of the onshore technical capacity, either for salt or for porous media, salt from literature, porous media from Hystories results, we find that there is much more capacity than the storage demand asks for. So we need to rank. We will need to select the best sites. And then we are giving data and inputs to help doing that. And we consider the fact that the capacity estimation, the technical risk when developing a site is very site-specific. The cost of developing a site is also site-specific. It's also cycle-specific. It depends a lot on the flow rate you will need. So we applied and we developed cost estimations that take into account this input data. We also built this complementary suitability mark that is kind of reflecting technical readiness or risk. We applied it to more than 800 porous traps, 18 bedded salt deposits, and old salt domes throughout Europe. And the finding raw finding we have is that, well, yes, it's not a surprise, but the cost increases significantly when we are going towards smaller capacities. That we can cover the storage demand with a levelized cost of storage that is as low as these values I just went through. And then suitability mark is higher for salt caverns than for existing porous natural gas storage and then for depleted fields. Thank you. Do we have time for a question?
Thank you. Maybe one remark. We have just had the discussion during the coffee break on the cycling, and I think what is important to have in mind is that we have a solely cost-based approach in this analysis. So what is not part of the analysis is actually what a lot of the storage operation today is about. So it's a trading to make use of the price arbitrage we have at the market. And these additional revenues, of course, are not part of this analysis, as well as the, let's say, the higher cycling numbers that could also appear, especially in case of the salt caverns, when we really use it for the trading at the market. So I think that is just one additional aspect that needs to be taken into account when looking at the final LCOS numbers you have presented. Thank you.
Thank you. We don't have that much time for other questions.